In today's video, we will be discussing about the first chapter of 9702 physics syllabus, that is physical quantities and units. So physical quantities and units. So base quantity. Base quantity. The base quantities are length, mass, time, electric current and temperature. So length, mass, time, electric current and temperature. And what are the base unit and the symbol? So the unit of length is meter, m, mass, kilogram, kg, time, second, s, electric current, ampere, A. Now A is capital letter, and temperature, Kelvin, K, where K is also capital letter. Prefix, symbol, and multiplying factor. So 10 to the power 12 is tera, T. 10 to the power 9 is giga. 10 to the power 6 is mega. 10 to the power 3 is kilo. 10 to the power -1 is deci. 10 to the power -2 is centi. 10 to the power -3 is milli. 10 to the power -6 is micro. 10 to the power -9 is nano. And 10 to the power -12 is pico. And tera is T is capital letter. Then giga, G is capital letter. Mega, M capital letter. Then all are small letter. That is kilo, deci, centi, milli, micro, nano. Now homogeneity of equation. So homogeneity of equation means that the left hand side base unit of the equation is equal to the right hand side base unit. So the left hand side base unit is equal to right hand side base unit. For example, here the left hand side base unit is equal to the right hand side base unit, so it is homogeneous. Here left hand side base unit is equal to the right hand side base unit, so this is homogeneous. While left hand side base unit is meter square, while the right hand side base unit is meter second, so this is not homogeneous. So homogeneous means that the left hand side base unit is equal to the right hand side base unit. Now for the equation S is equal to ut plus half at square, the unit of S is meter, U is meter per second, time is second, A is meters per second square, T square is second square. And if you cancel this and this one, then the unit becomes meter. So yes, left hand side base unit is equal to the right hand side base unit, so the equation is homogeneous. Similarly, for this equation, V is meter per second is equal to U is meter per second plus A T. So A is meter per second square and T is second. So per second square cancels with second and it would be per second. So meter per second. So left hand side base unit is equal to the right hand side base unit. So the equation is homogeneous. Similar for this equation, but here the equation is not homogeneous because the left hand side base unit is not equal to the right hand side base unit. Instrument and precision. So meter rule or for measuring tape. So for meter rule or for measuring tape, the precision is 1 millimeter or 0.1 centimeter. So for meter rule, it is 1 millimeter. For vernier caliper, it is 0.1 millimeter. And for micrometer screw gauge, it is 0.01 millimeter. So for meter rule, it is 1 millimeter. Vernier caliper, it is 0.1 millimeter. Or for micrometer screw gauge, it is 0.01 millimeter. And for meter rule, if we just convert millimeter to centimeter, then it would be 0.1 centimeter, 0.01 centimeter, and 0.001 centimeter. Precision and accuracy. So precision. So what is precision? Precision tells us how close the values are to one another. So precision tells us how close the values are to one another. Precision tells us how close the values are to one another. So how close the values are to one another. For example, this is our three values and they are close together. So this reading is precise. And for this reading, here we can see that the three values are further apart. So this is not precise. Similarly, if these readings are close together, for example this reading, so they are precise. And if the readings are further apart, then they are not precise. So precision tells us how close the values are to one another. So how close the values are to one another. For example, this is precise since they are close together. This is precise since they are close together. While this is and this is not precise since they are further apart. Accuracy. It tells us how close the values are to the true value. It tells us how close the values are to the true value. So how close the values are to the true value. For example, this is our true value this is our true value, and this is our true value, and this is our true value. So we can see that our measured values are close to the true value, so this is accurate. Similarly, for this result, we can see that our measured values are close to the true value, so this is accurate. And for this result, our true value is this value, while our measured values are this value. So this is not close to the true value, so this is not accurate. Similarly, our measured values are not close to the true value, so this is not accurate. So accuracy tells us how close the values are to the true value. It tells us how close the values are to the true value, how close the values are to the true value. Now, precise means that the values are close to one another, and accurate means the values are close to the true value. Accurate means the values are close to the true value, and precise means the values are close to one another. For example, here we can see that the measured values are close to one another. So close to one another means it is precise, and close to the true value, so this is the true value, that means it is accurate. Similarly, here we can see that the measured value is close to the true value, so this is accurate, but here we can see that the values are further apart. So values are further apart, therefore it is not precise. Similarly, for this situation, here we can see that the values are close to one another. Close to one another means the reading is precise, while the value is away from the true value, so this is not accurate. Then this is the true value, and since the measured values are not close to the true value, therefore it is not accurate. And since the measured values are further from one another, so further from one another or not close to one another, therefore it is not precise. Systematic and random error. So systematic error that is consistent in magnitude as well as sign. Error that is consistent in magnitude as well as sign. So error that is consistent in magnitude as well as sign. That means if the error is consistent, then it is systematic error. For example, here we can see that this is our true line. That means our true line have to be this line, but our measured values are these values, that our measured line comes to this line. So here we can see that the measured values are not close to the true line, or it forms a different line. So the readings are consistent. Here we can see that the readings are consistent. So the readings are consistent, but it is not close to the true value, and it forms a different line. So error that is consistent in magnitude as well as sign. So this reading is consistent, that means it forms a separate line, but it is not close to our true line, or it does not make our true line. So this is our true line, but that we're supposed to get, but we get this line due to systematic error. So systematic error is the error that is consistent in magnitude as well as sign. Error that is consistent in magnitude, so the error is consistent. So here we can see that for each reading the error is consistent. So systematic error can be fixed by fixing the instrument. So by fixing the instrument, or by using a different instrument, or by changing the experimental procedure. So systematic error can be fixed by fixing the instrument, or by using a different instrument, or by changing the experimental procedure. Fixing the instrument, by using a different instrument, or by changing the experimental procedure. And an example of systematic error is zero error. And due to the zero error, the readings are always greater than the true value or less than the true value. So due to the zero error, the readings are always greater than the true value or less than the true value. Therefore, it is called systematic error. That means the error with a consistent. So the error with a consistent magnitude and sign. So here we can see that for all the readings, the error is consistent. Random error. Here we can see that our measured values are these values. So as we can see that the measured values are these values, that means the measured values are scattered. And if we draw the best fit line, then the best fit line for this measured value is passing through the origin. Since the line is passing through the origin, so though the points are scattered, but by taking the average and drawing the best fit line, the error is reduced. So error that can be fixed, so that means random error can be fixed by taking average. So error that can be fixed by taking the average of the readings. So here we can see that the readings, and this is fixed by taking the average and drawing the best fit line of the readings. So as we can see that the readings are scattered, so the readings are scattered. But the scattered readings, from the scattered readings, if we draw the best fit line, so we can see that the best fit line passes through the origin and is a straight line. That means the error can be fixed, or the error is fixed by taking the average or by drawing a best fit line. So the errors are fixed by taking the average or by drawing a best fit line. The uncertainty, so absolute uncertainty means the approximate change in the value. So approximate change in the value. Then fractional uncertainty, approximate change in the value by the true value. Approximate change in the value by true value. And percentage uncertainty is the fractional uncertainty into 100%. That is the approximate change in value divided by true value into 100%. So percentage uncertainty is the approximate change in value by true value into 100%. So absolute uncertainty is the approximate change in value. Then fractional uncertainty is the approximate change in value by true value, and percentage uncertainty is the approximate change in value by true value into 100%. Combining uncertainty. Now for this part, you don't need to memorize this, you just need to understand this. So for sum or difference, add uncertainty. That means if suppose a is equal to x plus y, a is equal to x plus y, this is our initial equation. Then what is the uncertainty? So for sum or difference, we know that we need to add the uncertainty. So approximate change in a is equal to approximate change in x plus approximate change in y. Similarly, for difference, that is a is equal to x minus y, though it is a difference, but we need to add the uncertainty. So we need to add the uncertainty, that is approximate change in a is equal to approximate change in x plus approximate change in y. So whether we add or subtract, we need to add the uncertainty. That is, we need to add the uncertainty. If we multiply or divide, that is, if we multiply or divide, we need to add fractional or percentage uncertainty. That is, if we multiply or divide, we need to add the fractional or percentage uncertainty. So we need to add fractional or percentage uncertainty, both are the same. So for example, approximate change in a by a is equal to approximate change in x by x plus approximate change in y by y. And here is 100%. If we just consider this as percentage uncertainty, then 100%, here is also 100%. So now it becomes percentage uncertainty. That is, this percentage uncertainty and this percentage uncertainty. The 100% cancels, and basically the equation forms a fractional uncertainty. And for this fractional uncertainty, you need to remember that if two things are multiplied, that means two values are multiplied, then the uncertainty, the fractional uncertainties are added. If the two values are multiplied or divided, the fractional uncertainties are added. That is, approximate change in a by a is equal to approximate change in x by x plus approximate change in y by y plus approximate change in y by y. Similarly, if we divide x by y, then what is the uncertainty? It would be approximate change in a by a is equal to approximate change in x by x plus approximate change in y by y. Though it is divided, but we need to add the fractional uncertainty. That is, approximate change in a by a is equal to approximate change in x by x plus approximate change in y by y. Then if there is power, then the power comes front of the uncertainty, that is the fractional uncertainty. For example, if it is our initial equation, so what would be the uncertainty? Approximate change in a by a is equal to approximate change in x by x, and since there is a power, so power comes from and it is multiplied with this. Similarly, plus approximate change in y by y, and the power comes from and it is multiplied with this part. And if a is equal to x to the power m by y to the power n, then what would be the uncertainty? So since they are divided, so we need to add the fractional uncertainty. Since they are divided, so whether we multiply or divide, we need to add the fractional uncertainty. So we need to add the fractional uncertainty. There is approximate change in a by a is equal to approximate change in x by x plus approximate change in y by y. And since there is a power, so the power comes front, and it is multiplied with this part. These are the some estimations that you need to remember. These are the estimation or some approximate values. So these are some approximate values. For example, I just marked the important ones. You need to remember all of this, but I just marked the important one that you must need to remember. For example, the mass of a person. The mass of a person can vary from 50 to 100 kg, but it is given approximately to 70 kg. So mass of a person is approximately 70 kg, that is given. You can write 50 to 100 any value. Then the height of a person is approximately 1.5 meter. So the height of a person is approximately 1.5 meter. Then the walking speed of a person is 1 meter per second. It can vary, but the approximate value is written here is 1 meter per second. You can write any value, that is 1.2, 1.3, any value, but it is written here as 1 meter per second. Then the speed of the car on the motorway is 30 meter per second. So you need to remember also this one. And then the density of water. So density of water is 1000 kg per meter cube. Similarly, density of air is 1 kg per meter cube. Density of water is 1000 kg per meter cube, while density of air is 1 kg per meter cube. And then you need to also remember this, that the hearing range of a person is 20 Hz to 20 kHz. The hearing range of a person is 20 Hz to 20 kHz. Then for Young modulus, you need to remember the value. That is, Young modulus is some value into 100%. That is, it can be any value, that is 5.9 or 5.6 or 7.1 into 10 to the power 11. If it is multiplied with 10 to the power 11, then it is the Young modulus. That is, Young modulus is multiplied with, for Young modulus values, they are usually multiplied with 10 to the power 11. For Young modulus values, they are usually multiplied with 10 to the power 11, and you need to remember this. So you need to remember this very well, that the Young modulus values are multiplied with 10 to the power 11. You just need to remember this, and what is Young modulus, we will discuss this in our next topics. But for now, you need to just remember that Young modulus is something into 10 to the power 11. Then frequency of visible light, we will discuss this later. Then mass of 30 cm plastic ruler. So mass of 30 cm plastic ruler is approximately 1 to 100 gram. Mass of 30 cm plastic ruler is approximately 1 to 100 gram. Then the density of air. So the density of air is usually given as 1 kg per meter cube. So it can vary from 0.1 to 10 kg per meter cube. So usually it is given as 1 kg per meter cube. Then again it is given as 0.1 to 10 kg per meter cube.